Good morning, everyone. I hope I can be heard. Thank you for joining on a Sunday. So we will revisit what we did last time on segmentation briefly, and then we will move on to understand an important segmentation technique using deep learning called the UNet. And after we understand the UNet, we will study about the transformers today. And actually today is the last lecture, as you know. Okay. In regard to segmentation, what we understood was if you are given an image, what we do is we label that image with one single color for a region. That means a label, okay? The color represents a label for the wall area, for the chair area, for the floor area, and so on. That is segmentation. Actually, an important part of segmentation is binary segmentation, where you have an input image and you give it a binary label. That means something like foreground and background. So this one is actually called semantic segmentation. And we studied about object detection also. Then if you detect instance in an image, that means each human being, uh, each pedestrian, each car, that's called instance segmentation. And when you combine semantic segmentation with instance segmentation, that means you have per pixel labeling for areas like drivable area, that means ground, building area, trees, sky, and so on, plus detecting individually human beings, cars, and so on. We call it panoptic segmentation. This is a very important for self-driving and so on. Yeah, this is the segmentation thing that we studied. And if you remember, we studied very basic segmentation techniques like thresholding and region growing. That's where we stopped. So we will not go through all the segmentation techniques that I have. If you are interested, maybe you can look at it, and I can, of course, have another class and show you how this is done. So here we want to look at deep learning based segmentations. So, so now this one is called fully convolutional networks, or FCNs, for semantic segmentation. So again, what is semantic segmentation? What we want to do is give a label per pixel. So each of the pixel in the image, we give a label: background, cat1, cat2. Actually, this one is uh, the label for the dog. This one is for the label for the cat, and this one is label for the background. So you can see we have studied convolutional neural networks. In the convolutional neural networks, you keep on running kernels, and the uh, size of the feature map keeps on reducing and reducing and reducing. So you can see here, they have a feature map, which is a very small in spatial size, but that has 21 channels. 21 channels. So these 21 channels and this structure, they somehow expand to the size of the image. Consider that as some upsampling scheme where they expand it up to the size of the image. Now it has also 21 uh, channels, and these images, they have 20 classes, 20 classes, plus one for the background. This one is for the background. These classes and background. So if you create this ground truth structure, where one plane for each class, okay, the cat plane, the dog plane, the background plane, and other planes for each class. And if we subtract from what is predicted by the network, a similar ground truth structure, where, as I said before, we have one plane for each class a binary plane, then you can see we can construct an error function. We can construct a loss function there. And if you construct such a loss function, you can see we can get that loss to backpropagate through the network and correct the weights. So this is the general idea of semantic segmentation done through a deep learning uh, framework. Now, in this case, you can see the 1000 class one has been upsampled or somehow resized to the size of the image, and this one is for 1000 classes. Yeah. So the fully convolutional network, this FCN network, had some other things because they found out that for semantic segmentation, if you just use this upsample version from the final layers, the output is not so sharp. You can see the boundaries are not so sharp. So what they did was they got these inputs from the previous convolutional layers also, and they upsampled and combined. Upsampled and combined. When you do that, uh, so because we are getting from this layer, this has to be only upsampled 16 times. If you are getting from this layer, it has to be upsampled only 8 times to match the image size. So like that. So this combination gave rise to quite good boundaries between. Now this is a cyclist, as you can see, with the ground truth. Fully connected, fully convolutional networks for semantic segmentation. Don't say fully connected. Sometimes I also make that mistake. Fully convolutional networks for semantic segmentation. So you can see this is an important contribution showing how convolutional neural networks can be used for segmentation. So you can see the upsampling scheme that they do. They had this upsampling scheme. Okay. Then we move to this next very important network called UNet. So UNet is also similar to this FCN, but it has a very well-defined structure for upsampling also. So you can see, I will describe this briefly. Now in the UNet, it's a very famous contribution. It's from the Mackay conference. This is the topmost radiology conference in the world. Medical imaging, computer-assisted intervention conference, Mackay conference. We also have a paper there. Uh, this UNet paper was published there by this very famous German authors. Input image tile is input image is 572 by 572 to single channel image. Then what they do is they run convolutions. So you can see the convolution kernel size has reduced to 570 by 570. So from that, you can understand that they must have run 3 by 3 convolutions, right? We have done this before. And again, they do a convolution. So you can see exactly, verily they have run 3 by 3 convolutions. So after the 3 by 3 convolutions, they do max pooling. You can see this is the down pointing arrow is max pooling. So because of the max pooling, the size becomes half. 2 by 2 max pooling. And again convolutions, and again then max pooling, max pooling, max pooling, conv, conv. Then you have this up convolutions. Mm. How they do this up convolution, I don't remember. But if you like, you can read the paper and understand. But only thing that you need to understand at this stage is the size of the channel once again doubles due to that. So this one is sort of called a bottleneck layer. So the everything that you downsample sort of is represented there somehow. So you can see once again so-called up convolutions, I'm sorry, convolutions. And then the up convolution here, convolutions, up convolution, convolution, up convolution. Finally, the map size will be 388 by 388 of two channels to say foreground and background. They had an important addition to this called skip connections. You can see these connections. We have seen something like that in ResNet also, but it is not there. So you take a part of this. So this map size is 392 by 392. You get a 392 by 392 crop from the original one and then just put them together, concatenate. You can see that they have been concatenated. Here you can see from the input layers and these from the upsample layer. The two parts, the white part and the blue part, they are concatenated. Why? Because for segmentation, you need both global information as well as high resolution information from the input. That's why the concatenation happens through these skip conditions. So similar to FCN, now this also can give a semantic segmentation map, segmentation map in this case. So we can briefly watch their video also. I will briefly play that video, not fully.
Welcome to our presentation. We designed a deep convolutional network for the segmentation of biomedical images, which we called UNet. It learns to segment images in an end-to-end setting, which means a raw image in and a ready segmentation map out. The main challenges were that we had only around 30 annotated images per application, and we nearly always have touching objects of the same class that need to be separated by the segmentation algorithm. Here is the architecture of our UNet. Like all other convolutional networks, it consists of a large number of different operations illustrated by these small arrows. The input image is fed into the network here at the beginning. Then the data is propagated through the network along all possible paths, and at the end, the ready segmentation map comes out. Each blue box corresponds to a multi-channel feature map. The XY size is denoted here, and the number of feature channels is denoted here. Most of the operations are convolutions followed by a nonlinear activation function. In detail, it looks like this. It is a standard 3x3 convolution followed by a nonlinear activation function. An important design choice is that we only use the valid part of the convolution, which means that for a 3x3 convolution, a 1-pixel border is lost. This allows later to process large images in individual tiles. The next operation in the UNet is a max pooling operation. It reduces the XY size of the feature map, so I have illustrated it as a downward arrow. The max pooling operation acts on each channel separately. It just propagates the maximum activation from each 2x2 window to the next feature map. After each max pooling operation, we increase the number of feature channels by a factor of 2. All in all, the sequence of convolutions and max pooling operations results in a spatial contraction where we gradually increase the what and at the same time decrease the where. A standard classification network ends here and all maps all features to a single output vector. The UNet has an additional expansion path to create a high-resolution segmentation map. This expansion path consists of a sequence of up-convolutions and concatenation with the corresponding high-resolution features from the contracting path. This up-convolution uses a learned kernel to map each feature vector to the 2x2 pixel output window, again followed by a nonlinear activation function. That's it. The output segmentation map has two channels, one for the foreground and one for the background class. Due to the unpadded convolutions, this map is smaller than the input image. The segmentation of the yellow area uses the input data of the blue area. With an overlap type,
Okay. That must have given you some idea about what the authors themselves said about their work. So that is about the segmentation. Please go through the UNet video fully. After UNet, there have been many advancements. Um, uh, TransUnit. It has never been published, but people use it a lot. Especially the unit was designed for medical image segmentations. But as far as segmentation is concerned, so we have um, the segmentation works culminating with segment anything. It's a very good framework that you would use. So you can see it can segment anything actually. You can see they are able to give colors to each of these buildings. That means a segmentation. These are advanced networks. This is by Facebook, and there's a thing called segmenting 2 also that actually does the segmentations in the videos. I hope you can see this. Then they do other things also in this. That's about segmentation. So if you have any questions, so please ask about the segmentation. Some of those are extremely important operations. So we looked at the basic segmentation techniques like thresholding and region growing, and then we quickly jump to the deep learning based segmentation techniques. Okay, then we will look at the next set of slides that we have, the transformers. Um, so let's first understand what the transformer means, the so-called concept of the attention mechanism and how the transformers do this attention. We will understand the difference between the convolutional neural networks and the transformers and some applications of transformers. And we will look at finally a little bit of what so-called vision language models also. Okay. So there are so-called vision transformers called VIT and SWIN. We are going to look at them also. And then there is a thing called self-supervised pre-training done in this transform-based networks, Dino and Mascot encoders. We will look at them and briefly look at this also, how the segmenting works briefly. And this one we will not look at actually, alternatives transform architectures. But we will look at the context, which I highlighted sometimes ago. Okay, a brief comparison of the transformers and convolutional neural networks. First, if you take the convolutional neural network, they use local convolution kernels to extract spatial features hierarchically. So you run a convolution, again a convolution, and maybe then you do 2 by 2 max pooling, then again like that. So hierarchically, you have a collection of representation of features. But in transformers, you divide the image into patches and model relationship between these patches. So you will understand that when I describe that later. So in the convolutions, we say that there's a strong inductive bias. What that means is we say because we are running convolution kernels and we are saying that the relationship between local pixels is important by running a small convolution kernel. And we are saying that even if we translate the image, we must get the same output. Yeah. These are things that as human beings we know about images and we have encoded onto the algorithm itself. So this kind of a thing is called an inductive bias. The inductive bias that we have in our minds, we encode into the computational algorithm that we have. But the transformers do not have such a strong inductive bias. We call it a weak inductive bias. So it's a much more general computational mechanism than the convolutional neural networks. So when it becomes general, you have to train it. The things that human beings also know, for example, we know that the apple being here or there is the same thing, right? The same thing. But the transformers cannot have that idea, but the convolutional neural networks can have that idea too. So to give that idea to transformers, you have to give more data to train the transformers. So here you can see, typically they are trained with large scale data sets like ImageNet 21K and JFT 300M. I think this is a proprietary data set. So, and when you train with a large amount of data, so it learns all these things, and it is able to not have an inductive bias at the beginning, but learn what is there in the images to produce what convolutional neural networks can produce using this inductive bias. But the convolutional neural networks can perform well with moderate data sets like ImageNet 1000 and so on. So convolutional neural networks, they run convolution after convolution after convolution. At the final structures, they sort of capture the global dependencies through the hierarchical nature of these convolutions. We studied about the receptive field. You know that if the receptive field is this large, that information is captured in one of the cells in the final layer. So, but in transformers, this global relationship is directly captured through this so-called attention mechanism. We call it self-attention. So we will look at that when we go through. Now, if you talk about the computational complexity, these convolution layers are complex, but they are not very complex. So they are linear in the number of pixels. So if you have 10,000 pixels and the time for computation is 1 second, if you have 20,000 pixels, it will be 20 seconds. But transformers are not like that. They are quadratic in complexity. That means if you have 10,000 pixels and you double the number of pixels, the computations will quadruple. So that's the thing about the transformers. They are computationally complex. So to handle this computational complexity, people came up with different mechanisms. We will look at one of those mechanisms today. So when you run these convolutional neural networks, features often correspond to edges, textures, and hierarchical structures. These are attention maps, can provide insight into which regions model should focus on. So we will see some attention maps later. For example, if you want to detect a cat, maybe it will focus on the eyes and the facial features of the cat. Yeah. So if you look at the attention map, you can see the cat's face will light up. If you want to look at the giraffe, the particular pattern of the giraffe will light up. So this is called attention. Oh, I copied this again. Yeah. Performance improves with depth and width, but saturates. So you can see convolutional neural networks, when you increase the depth, performance increase. When you increase the width, also performance increase the resolution, also performance increases, but you cannot keep on increasing that performance. But if you take transformers, scales extremely well. This is the most important property of transformers. Transformers are so structured that when you can keep on enlarging and enlarging the number of weights, the size of the network of the transformers. So that's why the transformers were able to capture a massive large language model so that it can work like a human language model, ChatGPTs and so on. So today we will briefly look at the so-called InstructGPT works. ChatGPT exactly works, I do not know. So they have not revealed that also, as I know. Then the common architectures we have seen, the VGG, we saw the ResNet, EfficientNet, DenseNet we did not talk about. Those are the typical architectures in convolutional neural networks. If you take the transformers, vision transformer, DIT, swing transform, and so on. So we will look at this today and the swing transformer. So you can see a general comparison between the CNNs and the transformers. Okay. So we said that the transformers have a thing called attention. So in 2017 paper, which yeah, Ashish Vaswani wrote, the Google person, they construct the transform for natural language processing. So this is an example natural language processing to show you what attention means. Okay, so now if you take this sentence, for example, called in it has the word it. I ask you, what does it refer to? Take a time and think about it. Maybe can you ask in the first sentence? What does it refer to? The animal didn't cross the street because it was too tired. Yes, thank you very much. People are answering. Actually, it refers to the animal. It refers to the animal. So that means the attention score it has on the animal should be large in comparison with the other words. But if you take the second sentence, this it refers to what? The animal didn't process it because it was too wide. It refers to the street. So you can see based on the context, what each word should attend to is different. So transformers are able to capture this relationship because we give a large amount of text to the transform. Yeah. All right. So here are the so-called attention maps. You can see the strength of the attention is higher for the word animal and here to the word street. So I hope you get the idea about what attention means, but how you still do not know how the attention can be mathematically captured. So we will see how it is captured. Okay. So here's a picture of this world famous papers, transform architecture. So I think we should look at this paper before we proceed. This is that famous 2017 paper on transformers. It appeared in New Rips. Ashish Vaswani and so on, all from Google research. So you can see the uh, uh, Google's current language models and ChatGPT and all language models and even vision transformers and how the computer vision works now is now based on this attention is all you need transform architecture. That's why Google blames OpenAI for closing their sources and having a massive financial model for their work because they are based on the knowledge Google created, Google people created. So this is the paper, the architecture of that paper. Okay, we'll try to briefly understand that, not fully. So this has two parts. The encoder part and the decoder part. So what is an encoder? Now think about an image encoder. You have some image, a raw image, and you convert that to a JPG. It is a different set of numbers representing the image. So similarly, if you give an input sentence, actually we call them not words, we call them tokens. That means the sentence is broken down into slightly smaller parts than words. We call them tokens, and they are embedded, as we call them embedding. So they are converted into set of numbers, and then this encoding mechanism that Any of these things, they convert it to a different set of numbers, and we will see this so-called attention, how affects how that happens. Here you can see the encoded output is sent to the so-called decoder part. You can see it here. We'll understand it slightly better in the following slides. And then the output, which is shifted right, the output that is coming shifted right, is sent through this, and it is sort of combined in this multi-head attention. So this is actually called cross attention. So we will look at that later. Encoder-decoder architectures are there, as you can see. Attention is the only interaction between inputs. There are no convolutions. Three flavors of key value query attention. So we will look at the key, the value, and the query later. There are some hyperparameters. The size of this embedding, so they call it embeddings. The size of the embedding dimension, number of blocks, number of attention heads. So these number of blocks, and it says multi-head attention. In the multi-head attention, how many attention heads are there? Those are some hyperparameters, but the number of hyperparameters is not too high. Okay, so to understand the transformers, we will briefly look at the so-called recurrent neural networks that processes a sequence. So you can see, you can consider this as a sequence of words. Sequence of words x1, x2, x3, and x4, and they have some mechanism of holding some information about these words. Hidden state. And using these hidden states, so works on ordered sequences. This is a good thing, no limited by the fixed content size in principle. After one RNN layer, HT sees the whole sequence. But bad thing is, hidden states have limited expressive capacity, not parallelizable, need to compute hidden state sequentially. This was some bad thing in the prior to transformers recurrent neural network architectures. Then there is another mechanism called 1D convolutions. So we run a convolution kernel in 1D across these word embeddings. So works on multidimensional grid, that's fine. Pros, each output can be computed in parallel at training time. Bad thing, bad at long sequences. Need to stack many conv layers for output to see the whole sequence. So you can see when you looked at the convolutional neural networks, you saw that the receptive field scales linearly with the number of layers. So to have long distance attention, you should have massive number of layers in a convolutional neural network. Then the other one is a transformer. So this works on a set of vectors, so we will see that. All right. So basic transformer model is sequence to sequence architecture, uses only point-wise processing and attention, no recurrent units or convolutions. Okay, so we saw the encoder part and the decoder part. So there's a self-attention part and the feed-forward part. Feed-forward is, you can see, multi-layer perceptron. Self-attention part, encoder, decoder attention, we call it cross-attention, and the feed-forward part. Those are the parts of the encoder and the decoder transform. So encoder receives entire input sequence and outputs the encoded sequence of the same length. Encoder predicts next token condition on the encoder output and the previously predicted tokens. So you can see these are next token predictors. So if you think that token is slightly smaller than a word, if you think it's a word sequence, I am, the next word may be going. So you sort of predict that, the next word. So you can say here you receive the previous output. That's why it says condition on the encode output and the previously predicted tokens, and the encode output from here. Yeah. I hope this general diagram is clear for you. Okay, there's a slightly more detail. Here you can see the input sequence x1, x2, x3, x4. So consider them as words for now. And then the output sequence y1, y2, y3, y4. Consider them as words. So now the decoder generates a query describing what it wants to focus on. What it wants to focus on. So you can see this arrow, this line goes like that, right? Okay, so that is this line. So after generating this word by one, it sort of generates a query describing what it wants to focus on through this line, okay? Now, computes a dot product between the query and the keys generated by the encoder, giving alignment scores between source tokens and the query. So we know that when you get the dot product between two things, it sort of says the similarity and the weight of the similarity. So so-called query and the keys, we will look at the later slide slightly more detail. They get the dot product, and now it sort of has a weight that shows the amount of focus that this decoder output wants to have. Feeds the scores into the softmax to create attention weights. You know that through softmax we can give a probabilistic interpretation. We looked at softmax computation before, and sums the values generated by the encoder weighted by the attention weights, and then so you can see how this works in slightly more detail. Okay, now we want to pay attention to the key value attention model. So in the paper also there is an important equation. We want to understand this equation, this very famous equation. So you can see the query, key, and value. So you can see Q, K transpose. You can see query and the keys have been dot product, has been obtained, as we saw in the previous slide. And then that weighs the values. Sort of applies a weighting on the values. Okay. Okay. So here is the input. And we compute the keys using some matrix multiplication. So what is that matrix? We don't know yet. We will learn that through backpropagation. Okay. Then we have the x's themselves as values, inputs themselves as values. But we compute that by multiplying it with the values matrix. That matrix is also learnable matrix that you learn through this backpropagation mechanism. Then you have the queries, query vectors Q1 to Q4. And then what you do is similarities are obtained between the keys and the queries. Three keys, in this case, K1, K2, K3. Four queries, Q1, Q2, Q3, Q4. So therefore, these similarities must be 3 times 4 set of numbers E1, 1, E2, 1 up until E4, 3. I hope that this must be very clear to you. But there is an important thing in this. When you get the similarity, you have to divide by the, that is a finding of this paper, Vaswani paper. You have to divide by d square root is a number, is the dimension of the keys. So these keys may have, maybe this is 768 dimension or something. 768. So you have to divide it by the square root of 768. Okay. Then what do you do? So then we apply softmax on them so that you can interpret them as sort of probabilities. and then you multiply the values with those, and then for finally produce the y's. So I hope that the key query value mechanism of the transformers is clear to you through this diagram. This diagram is from Justin Johnson. Okay, how does the permuting the order of the queries change the output? If you change the order of the queries, this means Q values, doesn't matter because correspondingly all others will change. But how does the changing the order of the key values change? If you change the order of the keys and the values are so changed, there's no problem. But if you independently change the keys and the values order, there's a problem. Okay. Encoder self-attention queries, keys, and values come from the previous layer of the encoder in the encoder part, self-attention. So you can see the attention is there here, that one we are talking about. And then decoder self-attention values corresponding to the future decoded outputs are masked out. So here that we will see what masking out anyways, that is self-attention. Then finally encoder decode attention, this attention block. Queries come from the previous decoder layer. Keys and values come from the output decoder. So these become the queries. These become the keys and values. Okay. So we saw the attention, how that happens. Okay. So let's look at this further. So query vector, key vector, values vector, and so attention weights, output vectors. So to think about the masking, think about this example. So as the XV gives, first one is some special token for start, and the first word is this, second word is. This you can see, that's the output from there, and is. So the decoder should not look ahead in the output sequence. Then that's cheating. So when we are doing this, we put minus infinity here for this set of numbers, this upper triangle, so that softX will produce 0. So V3 cannot attend to this location. V2 cannot attend to this location. I'm sorry. This Y1 cannot attend to this location. Y2 cannot attend to. So you can see that it cannot attend to future. Okay. So I invite you to study more about the transformer. So I cannot give a full explanation. I'm not ready for that. But if you like this, you can watch online what people talk about transformers. Huge amount of knowledge about the transformers. But I think the most important thing about transformers, input size and the output size are the same. So therefore, you can stack many transformer layers on top of each other. Okay, so let's first look at the important contribution by Google, by Devlin and others, called BERT. Yeah, BERT. So this one, take the token embeddings. Okay, they are not actual words. They have been converted into numbers, and they are slightly smaller than words, although you see words here. So first one is called the class. He, be, let, you, leave. Now And then you have two masks. Some words have in masks, mask. And this is the sentence separator. Sentence separator. So task of this mechanism, the self-attention layers and so on, is to predict the masked words. He will be late. And you should leave now, like that. Predict the masked words. And also it also has to show whether the second sentence is actually the next sentence is of the first sentence. In the actual sentence sequence, the second sentence is the next sentence of the given the first sentence. So it's called NSP, next sentence prediction. So in this case, to train the encoder, pre-training task is the so-called masked language model, MLM, masked language model. It's a great contribution. So you can see the value of this. I hope you can see the value of this. So now one thing is that you cannot give labels to each sentence, okay? Because those are so many sentences are there in the human written text. So what they say is, okay, we take sentences. And like we train language to students when we were kids, our teachers also gave blank, right? I blank am, I blank going. What should be in the blank? Am. So like that, we were taught how to fill in the blanks. So we train the network also how to fill in the blanks. The good thing is the correct sentence we have because we already extracted that from a textbook or something. The sentences with field masks are there already with us. So therefore, what the network predicts, we can check whether it is correct and construct a loss function for that. Yeah. So one more thing is, what is this thing here happening here? Let's think about this. Now, assume that there are 30,000 words in English. 30,000 words. So each of these outputs will be 30,000 dimensional. So what that means is for each of the words, you will have a probability after softmax. So what that means is highest probable word is the one that is taken. So you can see the mechanism is very clear, right? Mechanism is very clear. So you through this self-attention layers, you compute a probability for each of these words out of 30,000. So in this masking mechanism, they masked 15% of the tokens. So the output is used to classify for the classification tasks. So here, if you want to classify, whether it's a positive sentence, negative sentence like that, there can be classification tasks also. So for that you can use. Okay, we'll move forward. That's BERT. Then GPT by OpenAI and others, GPTs, generative pre-trained transformers. So these are decode-only architectures. So you can see the start of the sentence, he will be late. So given the start, it has to say he. Given that word he has it has to say will. Given that word also will, it has to say be. Given that word also, it has to say late. Given that word, it has to say, okay, sentence is complete. So you can see the self-attention layer and you can see the so-called positional embeddings. You can see for these ones sentences, we have to say, okay, this is the first word, this is second, this is third, and so on. Some positional embedding has to be there. So that we do by using a sinusoidal cosine kind of a function. So we will see that later when we talk about the vision transformers. So this one is called next token prediction. It's a causal language modeling. So previous one, you can see it was a masked language model. BERT. Okay. So now that we studied about the GPT, we will briefly look at how the Instruct GPT works. From this, you can sort of understand how ChatGPT must be working, but it's a very incomplete understanding. This is from the OpenAI's website. So assume that they have a GPT, that previous thing that we have. So what they want to do that with that is this. Collect demonstration data and train a supervised policy. Okay, what do they do? So they have some prompts, sample from prompt database. For example, explain the moon landing to a 6-year-old. Like that, you sample a question prompt. Okay. Then a labeler demonstrates the desired output behavior. So some people went to the moon like that. Labeler demonstrate the desired output. So then you have a network it's called supervised fine tuning. So you can see the supervised output is available. The data is used to fine tune GPT-3 with supervised learning. Okay. So they say that they used about 40 people for this task. That's the first step. After that, collect comparison data and train a reward model. Train a reward model. Okay, let's see what this reward model is. A prompt at several prompt outputs are sampled. Prompt and a several model outputs are sampled. Explain the moon landing to a 6-year-old. First response is, for example, explain gravity, whatever. There are 4 responses, let's say. And a labeler, a human being, ranks this. Okay, D is better than C, better than, and like that. They rank them. When they rank them, this ranking data is used to train a reward model. RM, reward model. Yes. So reward model means you can say good or bad. That's enough. Reward model. You can have better reward models. For example, now if you're training a dog, if it does something good, we give it a biscuit or something. If it does not do it, we hit it a little. So that kind of reward model, right? Then finally, when you have the reward model, a step 3, optimize a policy against the reward model using reinforcement learning. So they are using this very powerful reinforcement learning. Now that you have the way to reward, you actually do it. The rewarding thing. A new prompt is sampled from the dataset. Write a story about frogs. Then so-called policy. Policy. That means given the current state, what must be the next? So that is called a policy. They use the so-called proximal policy optimization, PPO. You can read the PPO paper. It's a very important paper to read if you wish. I have the PPO paper, so it's so valuable on my desk. So a PPO paper, I suggest you to read, and if you read it, you will understand. It's not very hard to understand the PPO paper. Then you will sort of understand how ChatGPT's these optimization schemes work. After PPO, you know that DeepSeek came, DeepSeek used GRPO, Group Relative Policy Optimization, GRPO. So those things are very good to understand if you are keen about these areas. So once upon a time, this generates, and then this reward model will say, the reward model we have already learned will say it's good to bad. Actually, it's not good to bad, but it's a number. The reward is used to update the policy using RPO. Yeah. So this is how they trained the so-called instruct GPT. When a person gives an instruction, how it produces an output, they do trained it through this pipeline. Okay, now that's we looked at the transform architecture. We looked at few ways of using this transform architecture in language models. Now let's go to the how it is applied to computer vision, because that is what we are studying. Yeah. So now you can see you have a cat image there. So in the cat image, the question that we have to ask is, what are words? Because in the BERT or GPT, the inputs were words, tokenized words. Tokenized words embedded into some number. Embedding means it puts it put as a vector. Those are the inputs. For the cat image, what is the input that we should give to the transform? So actually they come up with a solution. You patch the image, you cut it into patches. And each patch you encode into a vector, or you can just rearrange into a vector, but that's not enough. And then you feed that as a word to the transformer model. So I hope if you understand the transformer model, if you understand how words are fed to that, now you understand how the VIT or the vision transformer works. Okay. So you can see the patches are given to the transformer as we gave words to the transformer, and it does the encoding. So let's look at the vision transformer in detail. Split the image into patches, feed linearly projected patches into a standard transformer code. So they usually patched for 14 by 14 into image. So we need the 16 by 16 to 156 patches to represent a 224 to 225 image. So 14 by 14 pixels. So 256 patches. So here you are showing 90 patches, but here actually you have 256 patches. So these patches are converted to vectors. Those vectors you can see here. This one, this one, this one, this one, this one, and so on. But this is not enough because in this scheme, that this patch is next to this. This patch is next to this. That kind of information is not there. So that's why they take the position, the X position and Y position, and they give some information of that position, where it is. Also here, like this 1, 2. 1, 2, 3, 4 is not enough, okay? 1, 2, 3, 4 is not enough. They convert that to some set of vectors, and they put those vectors of the same size as the same size for each of them. So they add the patch and position embeddings together, and then they feed to the transform encoder, and there's a multi-layer perceptron head at the end, and then it can predict the class, bird, ball, cat, chorus. This is the vision transform. So vision transform also uses the encoder block of the transform. Any questions about the vision transform? Okay, so let's move forward then. So you can see the different parameters of the vision transformer. Number of layers, 12, those transformer layers. Hidden size, we spoke about this size, the D, and we had divided by the square root of D when you get the key query softmax, that number. MLP size, multi-layer perceptron size, number of heads, number of 86 million. What is the thing about the number of heads? Sorry about that. Mm. What they do is, um, they use 8 heads. This is the original transformer paper. They use 8 heads. And this model dimension, D model, is 512. That 512 you take and divide by h and then get the dk and dv as 64. So you can see, rather than doing this uh, computation for vectors of dimension 512, you do that for 8 set of vectors of dimension 64. Computational cost is reduced, and these attentions in these different heads can extract information from so-called different spaces, different natures of information. Please, number of heads is 12 in this case, and the multi-layer perceptron size is 3072. I think here the MLP size, I'm not too sure which one they're talking about, but that's okay. So this is an ICLR paper by Dosovitsky, the VIT. The VIT trained on supervised fashion and fine-tuned on ImageNet. So you can see the transfer to ImageNet while large VIT models perform worse than VIT ResNets. We are pre-trained on small datasets. They shine when pre-trained on large datasets. Similarly, large VIT variants overtake smaller ones as the dataset grows. So you can see a lot of data is required. When a lot of data is there, they are much better. So you can see this ImageNet, ImageNet 21K, so-called JFT. So you can see the so-called VIT, and then the VITs, they perform better when the data sets are large in this column. And some other computation efficiency claims compared to ResNets. Okay. Now we looked at the VIT. The problem with the VIT is this. Now, if you have 16 by 16 patches, so we said that there are 16 by 16 patches, right? So each of these patches will have to be taken, and each of them will have to attend to each one of them. So first batch has to attend to 16 of them. Okay, 15 of them. Second batch has to attend to 15 of them. So you can see the computational complexity is like sort of 16 times 16. So that's why I call it quadratic in the number of patches. Quadratic in the number of patches. So if the image size grows, this is computationally expensive. Quadratic complexity is a bad thing. So that's why they came up with the hierarchical swim transformer. So here you can see they have, okay, the purpose of swim transformer builds the hierarchical feature maps by merging image patches, shown in gray, in deeper layers, and has linear computational complexity to the input image size due to the computation of self-attention only within the each local window shown in red. So they don't compute the attention with all these 16, but attention is computed within each of these local windows. Because of that, computational complexity reduces. But then there is a problem because you are not attending to other patches. So that's why in the next layer, you have sort of these blocks combining and then attention being applied. One more thing is now when this happens, in this layer, there is no attention bit from this to that. So for that, they have this mechanism called shifted windows approach for computing self-attention in the proposed Venn transform architecture in layer L left. A rectangular partitioning scheme is adapted. The self-attention is computed within each window. In the next layer, L+1 right, the window partition is shifted, resulting in new windows. The self-attention computation in new windows crosses the boundaries of the previous windows in layer L, providing connections among them. So these are the two main contributions of this. So you can see a picture of this hierarchical transformer swing. The architecture of the swing transformer, two successive swing transformer blocks, notation presented with equation 3. So you can see the patch partitioning in the color image, linear embeddings, and two swing transformer blocks, then patch merging, two swing transformer blocks, patch merging, six swing transformer blocks. And you can see how the resolution is reducing. Okay, so the results we will not concentrate on them. Yes. Okay, so I hope you understand briefly how the vision transformer works. So transformers are for mainly natural language processing, sentences, so sequences of tokens. So to construct that sequence of tokens in the vision transformer, what we did was we patched the image and added the so-called positional embedding and then fed that to the transformer. But we realized that it is a quadratic in the number of patches. So therefore, the swing transform architecture was proposed. Okay, now we will look at some self-supervised pre-trained architectures. So self-supervising is extremely important, as you can see. So the success of this ChatGPT and all these large language models is based on the self-supervising. That means the masked language model. So you take large amount of sentences, you mask out the words. The ground truth is available to you. You don't have to annotate. Yeah. But if you take a conversation sequence like the comments that people give for movies, and then you have to label them good, bad, neutral, good, bad, neutral, good, bad, neutral. So this labeling is not doable because you need large amounts of data. Labeling is not possible. So that is why these self-supervised objectives are extremely important, and it transforms the whole field. And that's why we have great things like large language models that can produce text like human beings do. Okay, so let's look at how this has been done in images. So in self-supervised pre-training, so you can see transformation prediction is one that we can do. So data and TX, and you have the network, and then you produce the T, predict the T. So like this, for example, now think about this. Now you have an image X, an image of a parrot, and you produce the original image, rotated image, rotated image, and then you run the same con, I think, connet, and then you had to predict 0 degrees, 90 degrees, 180 degrees, 200. What a cool idea, right? What a cool idea. You have the same images. You rotate. The angle which you rotate, you know. And by looking at these images, the network has to say 0, 90, 180, 200. That's a simple task. So with this, the network learns how the image looks like, right? When you give thousands and millions of images, the network will understand how to represent an image. Remember when we started these things lectures also, we said the name of the main conference, one of the main conferences in this area is ICL, International Conference of Learning Representations. We learn the representation, how to represent. Yeah, so you can see this is a powerful, powerful mechanism. But then people came up with other methods like Siamese network. So this like you do take the data and do one transformation on that, another transformation, and you run with the same network and the score should be similar. Rotation is just one of them. But you can do other things like you can add some intensity, you can do different kinds of transformations. So here is an example of a transformation. Color transformation, and you move the image a little. Cropping. Representation should be similar for these things. And representation should be different with this image. Because these are from different class. So like that, you use this Siamese networks for that. Okay. So then Dino, self-distillation no labels is powerful contribution. So you can understand what they did. So they had some kind of an image. Not some kind of it has an image. So they have the transformation 1, transformation 2. Okay. So they had some so-called teacher with parameters theta t and whatever that center means, and so it produces this one, t2. And then you have the student with parameters theta s, parameters of the student network, and he produces P1. This P2 and P1 must be the same because it's going through transform versions of the image. And therefore, you can think about the cross entropy and use that as an optimization objective. We illustrate Dino in the case of one single pair of two weaves. Two weaves of the same image, x1 and x2 for simplicity. The model passes two different random transformations of an input image to student and the teacher network. Both networks have the same architecture but different parameters. The output of the teacher network is centered with a mean computed over the batch. Each network outputs a k-dimensional feature that is normalized with the temperature softmax over the feature dimension. Their similarity is then measured with cross-entropy loss. We apply a stop gradient operator on the teacher to propagate the gradients only through the student. The teacher parameters are updated with an exceptional moving average EMA for the student of the student parameters. That's done later. So there are other things about this Dino tricks to avoid collapse. Student teacher training will with distillation loss cross entropy on top of our softmax outputs. Apply centering to the teacher output followed by sharpening softmax will with low temperature. Stop gradient. Do not update the parameters of teacher branch with back propagation. Instead update teacher parameters the exponential moving average of student performance. So this is actually a pseudocode of that. You can see how simple that is. So you can see the different two networks, the GS, the student, and the GT teacher, sent operation, TPS, TPT, student and teacher temperatures, one M network and center movement rates. Get that. So you have an image X and you augment it, and you produce X1 and X2. You send it to the student and produce S1 and S2. Send it to the teacher and produce T1 and T2. And you produce a loss, cross entropy loss T1 and S2, T2 and S1. and then back propagate only to the student. Update parameters. So ground truth GT parameters, not ground truth, as teacher parameters, student parameters. You can see exponential moving average means this. Then centering operation. Then they have given the definition of this HTS also. So you can see with a very simple mechanism, you can use self-supervised learning. Yeah. You did not need the image labels of the images in this case. So with that, they have classification, grid classification results. And then they understood that the self-attention from vision transformer with 8 weighted batches trained with no supervision. So you can see self-attention. So you can see the attention is map is high here. Because it is toothbrush that we are concentrated on. Brush class and the ship attention maps. You can see through this mechanism, the network has learned to focus its attention on the important features that are useful for the classification, as giraffes, as ship, as toothbrush, as Buckingham Palace or something. Attention maps of different heads. The different heads are there. So you can see the different heads have learned to concentrate on different things. Then they had Dino V2 also. We will not look at Dino V2. You can read it on your own. Then we can look at the self-supervised training, the other one. By mask image model. So this is, you can see, image, part of the image has been masked. Like we masked parts of the sentence, now a part of the image has been masked. Now the task of the network is to predict the full image. But the full image we already have as ground truth. And then we mask, right? So you can see, without knowing the label, we can produce training results in this. Yeah, this is the true output. So we force the network to produce this kind of an output. So you can see the MAE architecture. This is also by the Kai-Ming He, the first author of the ResNet paper. So you can see the mask image. Those patches are lined up and you encode them. And to the decoder, we feed that with the mask tokens, and it has to produce the this full output. If the full output is not produced, we incur a loss and backpropagate through the weights of the network. So you can see so many images and mask image and the reconstructions of the MAE. They have like great reconstructions, right? One or two may have problems. Okay, so we will not look at the results. So they were able to do classification and object detection and all sorts of things. Different applications of MAE. Okay. So then we will briefly look at the mask to former and the SAM also. I think that one is not there. So we look at the detection transformer. This is a transformer that is used to detect objects. So from last week, you remember the object detection means you have to draw bounding boxes. How this works is, first of all, it has a CNN to reduce the size. And then it has a feature vector Then you have transform encoder decoder, and then these have this box predictions. That means the coordinates of these boxes, or whether it's a box or no, whether it's an object or no object. So it produces uh, and then you have the ground truth, and we have to do so-called bipartite matching loss, and matching between the predicted boxes of the network and the ground truth boxes is not easy because you do not know which box matches with which box. So therefore, for that they use the so-called Hungarian algorithm. So Hungarian algorithm is able to take two sets and optimally match them. Optimal match. Which one should go with which? That one Hungarian algorithm can do. It's not a deep learning algorithm. So you can see this one. So you have the CNN, and it predicts a set of weights, and then vector, image feature vector, and then position and encoding is there. Transformers need that, and then you add them and feed it to the transform. It encodes. And the transformer decode is also called object queries are there. And then you have a feed forward network to give the class box for this. That means the center and the width and the height and the class name. Class name called this bird cow sound. Then you have to compute the loss. You have to use this Hungarian algorithm and compute loss. So this is the mask former. Actually, I'm not ready to describe this mask former. So if someone is interested, I will go through it and explain. The segment anything model. The thing about segment anything model is it has to segment anything. What that means is uh, showed you the its segmentations. It almost segments anything in the image. So now in the segment anything model, it's by Facebook, very recent one, 2023. You can give the as a prompt. Now in the chat GPT also we give a prompt. Here you can give the prompt as these dots, key points, or you can give a box, or you can give a segmentation mask, or you can give a sentence, and of course an image is given. Based on this prompt and the image, it will segment. So the prompt is encoded somehow. You give the image is encoded somehow, and then the lightweight mask decode is there, and then you get the lightweight masks. We aim to build the foundation model for segmentation by introducing three interconnected components: a prompt, promptable segmentation task, a segmentation model SAM, and that powers data annotation and enables zero-shot transfer to a range of tasks via prompt engineering and data engine for collecting. I don't remember SA1B, our dataset over 1 billion masks. So this data engine part is also very important in the segmenting model. So they had the model and they had the data, and they did some segmenting model, 1 billion masks, 11 million images, privacy respecting licensed images. Uh, so they with some training they had the model, and that model itself annotates, and then they had a sort of an engine that does the annotation by itself. So this is a big contribution to the segment ending model. Uh, if I want to look at that paper. The sample, not the sample one. This engine. You can see the masks. Okay. how do you do the data engine thing? As segmentation masks are not abundant on internet, we build a data engine that enables the collection of our 1.1 billion mask dataset SA1B. The data engine has three stages: a model-assisted manual annotation stage, to a semi-automatic stage with mix of automatically predicted masks and model-assisted annotations, and fully automatic stage in which our model generates masks without annotating input. We go into the details of each next. In the first stage, resembling classic interactive segmentation, a team of professional annotators label masks by clicking foreground, background objects, pointing using a browser-based interactive segmentation tool powered by SAM. Masks could be defined using a pixel precise brush and eraser tool. So like that, humans do that first. Then after that, semi-automatic, and then finally, fully automatic. So if you are interested, you can uh, look at how they do that. Then what is a zero shot? Intuitively, our pre-training task endows model with the ability to respond appropriately to any prompt at inference time. So you can see the previous image classifiers or segmenters can segment a previously known object, okay, classify dogs. But here, if you give any natural language description, it should be able to segment that. Any mask, it should be able to segment. How do they do it? Because they have a representation for the language also. So using that, they are able to do that. So we are looking at briefly about the vision language models also today, and then you will understand it slightly further when we look at the CLIP model. Now you can see today's lecture is slightly research oriented and slightly advanced. Obviously, it's the last lecture. Segmented model. A segmented model overview, a heavyweight image encode outputs an image embedding. This is the image embedding. This is the image that can then be efficiently queried by a variety of input prompts. So you can see it can be point, box, next, mask, point, box, text, or mask. So this has an encoder and then the mask decoder. And then combined with this, it will produce the mask. For ambiguous prompts corresponding more than one object, SAM can output multiple valid masks and associate confidence scores. So there are some alternatives to transform architectures like hybrid transform architectures. There are things people write beyond transformers, and then look at the connects themselves in the connext paper, and these connects seem to be able to match the performance of the swing transform. So that's what I want to do up to now. So let's take a break. We will meet at 35 for 10:50. Yes. Thank you very much. We can take a brief break. Welcome back. Thank you for staying in the class. So we will look at vision language models now. What this means is both the images and the text can be input to these models. So now you know that these large LLMs like Gemini and ChatGPT and so on can take images also. So how that kind of a thing works. First, we will look at the CLIP model by OpenAI. This is a 2021 work. So we'll understand how that works. Then you will get sort of an understanding how these vision language models work. Okay. Although there is one way of getting that done. So this is called the so-called discriminative way of getting that done. And there's a generative way also. So here you can see an image is there. And there's an image encoder. What does it do? For each image, it will produce some vector. Some vector. How many dimensions? We don't have to talk about it. It's a reasonable number of dimensions. For the second image, also a vector. For the nth image, also a vector. Each image is paired with a textual description. Pepper the Aussie puppy, and so on. So for that, there's a textual encoder, and image 1's corresponding caption will be encoded as T1. Image 2's corresponding caption will be encoded as T2. Image n's corresponding caption will be encoded as Tn. Now, we will try to get the similarity between caption of image 3 and caption of image 3 and the caption of image 2. Caption image 3 and the caption of image n. Another example, image n and caption of image 3. I hope you understand what these things mean. So we get the similarity. So what is the way of measuring similarity between two vectors? Okay, let me ask that question so that I know that you are paying attention. Similarity between two vectors. Give me a brief answer. Excellent. I have received answers. Cosine similarity. You get the dot product between them and divide by the magnitudes, right? To get the cos theta. That's how we measure the similarity between two vectors. These are exactly those numbers. I1 dot I3. In dot itn. Similarity. Okay. Now, this is the most important concept. We train the text encoder and the image encoder in such a manner the vector encoded by the image encoder and the vector encoded by the text encoder are similar if they correspond. In other words, encoding of the image I3 and the encoding of the text of the image 3 must be similar. That means in this structure, in this n by n thing, the diagonals must be high. Only the diagonals must be high. See how easy that concept is. So that even the image is encoded by the image encoder and a vector is given. Description of the corresponding description of the image will be encoded by textual encoder and you get a vector. Those two vectors have to be similar. So you can see the image embedding and the textual embedding have been aligned. This is what we call alignment, cross-modal alignment. They are called cross-modal. Why? Because we have the image modality and the textual modality. So cross-modal alignment. Cross-modal alignment. So when we look at Dino and so on, we took the same image and got transformed version and aligned within the same mode, right? Single modal alignment. Here we have cross-modal alignment. So this is the mechanism. Jointly trains an image encoder and a textual encoder to predict the correct pairings of batches image text. Training examples. At test time, the learned text and encoder synthesizes a zero-shot linear classifier by embedding the names or description of the target dataset classes. Now you can see zero-shot testing. Zero-shot testing. Let's look at that. Zero-shot means if you have a particular image and you want to get it classified as an image of a 3-wheel or something, you don't have to train it with those images. You can just directly get it classified. So how do you do it? Okay. You gives an image of an unknown class or something, this one, and the image encoder will encode that. And you take all the classes that are available, and then you append that with a photo of that class, photo of a dog, photo of a bird, a photo of a car, and so on. You construct that sentence. You can see you can construct that using just a Python script, and you encode that, and you have encodings, whatever encodings. And you get the similarity between T1 and I1, T2 and I2, T3 and I3. Sorry, I3, I1 and T3, I1 and Tn. The maximum will correspond to the correct description. Dog, a photo of a dog. Can you see that? Can you see how nice this concept is? Yeah. So clip is available for you to use. You can use it and test it. So in algorithmic form, it's very easy. So image encoder, this one, and the textual encoder, this one, yeah. And you get IF by encoding the image, and you get TF by encoding the text. And what we do is we get the dot product between IF and TF, and we have the some normalization, and you get IE and TE, weights are there, and then you compute the dot product between IE and TE, and you raise it to the power of T also, and we get the so-called logics. That's it. But you have to have millions of labeled images for this. Okay, so I think you understand the clip model. It's very important to understand. So this is you can see is very nice, easy to understand vision, and very powerful vision language model. A lot of people use clip in their work. Okay, now we look at one more thing called Lava model. So this is an end-to-end trained large multimodal model. Multimodal means image and text multimodal model that connects vision encoder and an LLM for general purpose visual language understanding. So take a large language model. Large language model. So what this large language model can do is, if you give it a sentence, give it a sentence, and of course you have to encode it in such a manner, and then it will be able to produce language output. Yeah, language output. So they use language only GPT-4 to generate multimodal image instruction following data. That's something else. You have the vision encoder. What is a vision encoder? It takes an image and represents that with a vector. So that is this one. And then you have you project that by a matrix multiplication into the space of the language. Now I think you understand what the space of the language is. It looks like a vector representing a language input. But actually it was generated using an image. Similarly, you have the language instruction also. The instruction that you give, what is this image? Describe this image or something like that. Yeah. So I think we can do that using ChatGPT, for example. Let's do that so that you understand practically what you mean by this is not the Lava model, but ChatGPT, that's okay. Okay, we can use Gemini, for example. So we download an image. So some random image. upload that image. So you give the language query, right? Then it will produce a language output. Beautiful, right? So that's the kind of thing we are talking about. So you can see the image has been encoded. So so you can see the image visual features are there. Here, that has been projected onto language embedding tokens. So you can see that this is image represented like language tokens. And the language itself of the query, that the sentence that I typed. And then based on this, you produce output. These are words. So GPT assisted visual instruction data generation is also there. They're using the captions and boxes from GPT-4 to generate questions. After a few manual responses, conversational, detailed description, complex reasoning, GPT-4 generates responses. So this kind of the language generation they use is one of the main contributions of the Lava paper. Step 1, pre-train the feature alignment. Keeps both visual encoder and LLM weights frozen. So uh, you can see, so here you see they use clip. This for the language model they use Vicuna. And this is frozen. Vision encoder clip is also frozen first. And maximizes the likelihood of with trainable parameters, the projection layer. So they somehow make this projection layer learned. That means the images are encoded similar to the words. Then after step 2 is update both the pre-trained weights of the projection layer and LLM. So they update this as well as this. So for example, user, what is unusual about this image? Then the Lava will respond, the unusual aspect of this image is a man ironing clothes on the back of a minivan or van. This is not a whatever. Yeah. Okay. So you sort of understand the vision language model. So this is a generative one. This we can see this is a discriminative one. This cannot generate language, as you can see. This can classify an image. This can generate language. Okay. Then these Qwen models are there. They are also very good. These are by the Alibaba. So they have the visual encoder, a cross-modal projection, and an LLM. Similar to the Lava model, right? So when you give an image or I think images or videos, when you give them, you have a visual on encoder. So those are encoded in picture 1, picture 2, picture 3. So those are encoded into tokens. And videos can be encoded in tokens. And yeah. This is the LLM, large language model decoder. Fine-grained on perception, window attention in the visual encoder, dynamic FPS sampling. So those are the features of that's there. Flagship is Qwen 2.5 vision language 72 billion. You have 2.5 vision language 7 billion and the 3 billion parameters, number of parameters. Yeah. So these are this another model. So that's all I want to talk about the vision language models. So we started with the transformers and we understood the transform mechanism. Then we realized that you have to give a sequence of tokens combined with positional embeddings to transformer so that it produces a sequence of another tokens. And then we looked at the BERT model and the GPT model and briefly understood how Instruct GPT works. And then we understood how this knowledge can be incorporated into computer vision using the VIT, Vision Transformer. Then in the Vision Transformer, you divide the image into a set of patches, and those patches are tokenized and sent to the VIT. of course, with positional embedding. So I did not talk about positional embeddings too much, but that is a very important aspect of that. And then after VIT, we looked at the VIT's computational complexity being quadratic in the number of patches. And because of that reason, we talked about the Swin transformer, which using the local window attention reduces that complexity. So afterwards, we briefly looked at vision language models. The vision language models, they can combine images and text. The mechanism is to align them in some space. So usually there are discriminative models like CLIP and the generative models. So in these generative models, they align them in the language space. I hope that these things are clear for you. I hope you understand that a lot of things are there. The space is huge. Space is huge, and a lot of work can be done in this area. Mm, Now, one more thing is like you have these large models, for example, Quen 2.5. So you go to Quen, you can give an image like the previous image. Let me give a different image. Where's that image? Oh, did I save it? I didn't. No, we can't take an image in that. Upload an image. We'll try to document. Let's see what Quinn says. Quinn says. They will start playing basketball. This image I gave. See, amazing, right? Here's why. Oh my goodness. Whatever. One thing is you can train these model. You can fine tune these models to suit your requirements. So if you want to fine tuning visual language models, um, you can read these articles and see you can get a simple language model and fine tune them. So I don't know which language model they used here. Uh, I think they used the so-called 5.3 model. This is from Microsoft. So this is an example. Many models are there like that. But when you do that, there are things called quantization and then low rank adaptation. So those also we have to understand. And then finally supervised fine tuning using the data of our own, data of our own. So what is LoRa? So if you take LoRa, uh, you can see these transformers, they have a so-called QK, WK, WQ, WV, those matrices. Those matrices are usually large. Then not extremely large, yeah, large. So what these people do is rather than changing the values of all these weights, that's called fine tuning, they decompose that into two products of two matrices, A and B. So this is called low rank decomposition. I think you understand what happens there. Uh, so in this diagram, you can see you have the so-called singular value decomposition. You can decompose into U and V matrices and a diagonal. So the number of entries in this diagonal defines the rank. So they do this low rank decomposition, and those they have small number of weights because of that. So this is one they fine tune, and then they add. This is what they fine tune. So perhaps you can fine tune both of these. Of course, this general matrix is kept frozen, or you can fine tune only the decoder, keep the encoder frozen. So this is LoRa, and then there's quantization. Mm. Let's ask ChatGPT itself. Uh, Search. So quantization, a process that reduces the model's memory footprint computational needs by converting its weights to a lower precision format, like floating point 32 to int 8 to int 4, during or before fine tuning. So these are there. This LoRa based fine tuning is called parameter efficient fine tuning, PEFT, and also they have the quantization. So this person's videos are usually good. Maybe some of you have watched this, Krish Naik. So maybe uh, you can watch his videos and gain some understanding about how to fine tune these large language models. Yeah. So you can see a quantized model, a low rank, and then of course the supervised fine tuning, SFT. So running these things is quite easy. You can run these things and see. Uh, and PEFT library has been imported for LoRa based fine tuning. Bits and bytes for quantization, I think. We can see load in 4-bit true. Okay. So I hope you understand what I wanted to say here. Fine tuning means now you have a vision language model that works for general things like Quen 2.5 vision language will be model. Now you want to get it working for your own data set better. That's called fine tuning. So this is the process for that kind of fine tuning. This is very important knowledge. If you know this and you have proficiency in getting a large language model or large vision language model and fine tune it, a lot of opportunities are there to earn finances out of this. Okay. So one last topic I want to briefly look at is about diffusion models. Um, so if you take Google Whisk, I don't have access to Midjourney, but if you take Google Whisk, you can generate images. Something like that. Some prompt. Amazing, right? Amazing. Unbelievable, right? So now there are video generators also. Yeah. These are videos generated by this Sora thing. Unrealistic images can be generated, unrealistic videos. Unbelievable, right? Unbelievable. Unbelievable. Yeah. This is by OpenAI. Okay. So yes, I want to briefly talk about how we generate images. I won't go into detail, but I hope I can talk about it. Do I? I don't know whether I prepared a lecture for that. Yeah, briefly. A lot of details are there, but I will not go through all the details, but I will briefly talk about it, how images are generated. So now the images are generated using so-called diffusion models. So you start with some noise and then you finally end up with the image. Start with some noise, you finally end up with that image. So how do you do this? This is very simple. You start adding noise to the image. Add noise to the image. Okay. Add noise. I'll write noise. I'll write sigma. Add noise to the image. Again, add noise to the image. I will just represent this. Okay, add noise to the image. Again, add noise to the image. Again, add noise to the image. Now you can see the original image is there, noisy image is there. Original image that this step is there, noisy image is there. Original image that this step is there, noisy image is there. So if you learn the reverse process, you're done, right? If you learn the reverse process, how to go from here to there, how to remove noise, yeah, you come up with a network that understands how to remove noise. Then you are done. Then you start with noise. It will remove, and you have this nice image. So starting with noise, you can generate an image. This is the diffusion model. So this is called diffusion because it is related to the diffusion equations in the physics, in physics. Okay. So it's generative. You can see it generates an image rather than discriminates between two classes. Generation learn to sample from distribution represented by initial training set. So you can see this is called conditional generation. So the previous one was just based on noise. This one noise plus a name of an image, goldfish. These are the generations. Indigo, whatever. These are the generations. These are these text. These are the generations. Text generations. Beautiful dogs. Text generations. condition generation. And then your condition can be hand sketch. Your condition can be a pose network. So pose default thing that you get is, and then with the prompt also. This is like this kind of prompt. Beautiful, right? So different kinds of other style answer. Swap sunflowers with roses. Add fireworks in the sky. Replace the fruits with a cake, and so on. Yeah. So initially, these kinds of things were done with generative adversarial networks, as you may have heard. So in the generative adversarial networks, in 2014 work, I think, you have a noise one, and then with the noise, you generate an image. This is a generator. So generate a fake image. This is a fake $1 bill. I don't know why you want to fake a $1 bill, $100 bill, yeah, maybe. And then you have the real $100 bill also. And there's a discriminator that's like a policeman. This policeman is experienced in detecting fake. So he will use his glass to look at it and say real or fake. Yeah. So usually now the printer, the fake money bill printer will print a bill. It looks horrible. And the policeman says fake. So, but then this man will learn. This man will improve his techniques. Improve his techniques. And someday, and you see, he knows whether the policeman said fake also. Someday he will print it so nice that the policeman will not be able to identify. Policeman will make 50% of error finally. Random. He cannot identify whether it's fake or real. That means that the generator, the printer, has become extremely good. But the policeman will also become better. So when they both become better, the generator will become extremely good in producing fake $100 bills that look $100 bills that look exactly like the actual one. So in other picture, so input dimensional noisy vector you input, and there's a generator, and then it generates images, fake images. Then the real images are there. The discriminator, the policeman, compares them and say real or fake. These are generative adversarial networks, and this is the first author of that, Ian Goodfellow, and yeah, he has produced this kind of survey also on that 4.5 years of GAN progress, face generation. So GANs have also done well. Yeah. Okay. Then after that, these denoising diffusion probabilistic models came, what I described earlier. With this, we present high-quality image synthesis resulting using diffusion probabilistic models, a class of latent variable models inspired by considerations from non-equilibrium thermodynamics. Our best results are obtained by training on a weight variational bound design to a novel connection between diffusion probabilistic models and denoising score matching with Langevin dynamics. Honestly, I don't understand that. I didn't read the paper, but you can see the method is what I described earlier. So briefly, I'm showing this method. These slides are from Setnal Nick. So you can see the noisy image XT. Then this is the good image. So you can see this is given xt minus 1. How do you get xt? As a noise addition process. This is the reverse process that we want to learn. That's their one. So I will not go into detail of that, those algorithms. And then this one, 2022 contribution is also a great contribution by Romba. These called latent diffusion models. So here the key idea is separate encoder and decoder to convert images to and from a low dimensional latent space and run uncacheable diffusion models of latent space. So they have an encoder and a decoder, and this is in the latent space, which is of very low dimension than the image. So you can see much more advantages than the previous early method. So there you can see they have the unit, what we learned there. So it's called stable diffusion because the company is stable diffusion. Not there's nothing stable in that. So these are the main frameworks that generate images. So people built on top of them to generate commercial versions of image generation. Okay, those are all the topics that I want to cover. I'm trying to see whether I missed anything important. Fine-tuning LLMs, vision language models. Yes. Yeah, those are the topics that I wanted to cover. So now we have about half an hour left. So now I like to open the floor for any questions that you have. I have some knowledge. I don't know everything. I also have knowledge gaps. What I know, I can tell you uh, about these things. So this is the most exciting field in the world. As you know, I think one of the most lucrative fields in the world right now. Um, if you know how to use these large language models, if you know how to use vision language models and fine tune them, and if you, I mean, this is great income can be generated with these things. Um, yes, I also have the ability to connect you with people who need that kind of services. But one thing is you have to show the proficiency that you have, that you know how to do these things. Because learning them needs some time investment on your end. Uh, yes. So the major application areas are image generation, video generation, self-driving, surveillance. That means detecting things when using large number of CCTV cameras, porting these algorithms to edge. That means running them in devices. Mm. And then low quantized computations. We already saw the QLoRa paper. I mentioned about that. And you can see uh, parameter efficient fine tuning and quantized models and uh, what are the effects of this quantization, then safety of these models, how these models can be attacked, and how these models can be applied in other domains. Um, for example, that now you have a communication system and you send so many symbols across the network, right? When you want to communicate messages, but can't you have an encoder in one side and the corresponding decoder in the other side, and you only say send the latent vector so that it can be generated, the message intended can be generated from the other end. So these kind of things are actually of great interest these days. Video generation, 3D. Oh, I did not speak about the 3D. 3D is also a very big field. Uh, Maybe you know that uh, it's if you take this this one, they are using so-called NERF, neural radiant fields to generate a 3D model of this scene. You can see the depth map here, the far away red and close by blue. So you can see the 3D of that vase and the table. So this is there. And then after that in 2023 came 3D 3D GS, 3D Gaussian splatting. I don't know whether any images are there in that. You can see these are Gaussian splattered. So think about those are these things are constructed using three-dimensional Gaussian balls. They're like fuzzy balls. They're a collection of millions of them. Millions of them. This is a different technique than the previous one, NERF. So we also worked on finally a project on this, and we produced good results. We have paper, but the paper got rejected. So you can see the generations. Yeah, generations are beautiful. Blurriness is gone. So NERF and 3D Gaussian splatting and 3D object creation, generated 3D models. So like that. Those are those of interest. Um, let me show a slide from somewhere. Uh, I cannot find it immediately. I need the slides for that. I'm sorry for not being ready for this, but yeah, these kind of things. You can see text to 3D generation, text to 3D. These are very new things. Actually, students gave me a gift. What they did is they took an image and they lifted it to 3D. Now online you can have those, and then they 3D printed. Beautiful, beautiful religious statue they gave me. So sketch to 3D, then finally image to 3D. This is what the students did. So it's called trellis. Yeah, that's what I wanted to show you. So that's 3D. These are very important in the movie industry and so on, robot navigation. Yeah, 3D things. That's all I want to discuss actually. I want to stop now and let you ask any questions. Yeah, please go ahead and ask questions. I don't think, although even if I give time, you will join to ask a question. So maybe today is the sort of the last opportunity for you to ask questions. About the exam, I will upload some more tutorials. I uploaded one so that you can get some questions from those so that you can get the pass mark, but there will be some, of course, challenging questions also. One assignment has been uploaded. These assignments are there for those who really want to invest time and learn the skills. But I know that using ChatGPT and so on, you can get the solution. So therefore, I will not give too much weight to these assignments in the grading process. But remember, without doing the assignments, you will find some questions difficult at the exam. So I will check whether you have actually done the assignment by asking specific questions that really need the knowledge of this assignment. I have uploaded one. I will upload two more. So if you need answers to those tutorials, please let me know. I can have another Zoom session. Although today is the last class, it does not matter. I can join a Zoom session and do some of those questions for you. Yes. So any questions or comments, I welcome. We can have a small discussion. We have time. Question: the most of the image generation models require hardware required. Can we use edge devices like mobiles for this? That's a good question. You need the GPUs for this. Mobile-based image generation. Actually, I don't know the answer. I have to check whether it's possible to do use the mobile. But the mobile is also very complicated. As you can see, mobiles also have neural processes for the forward pass, although they cannot backpropagate. For the forward pass, hardware is there in the mobile. So most probably some generation can happen in the mobile. It's also very powerful. But I have not done that. So therefore, I don't have an answer for that question. It's a good question, actually. So if you want to do that by yourself, I think you should use a framework that actually accesses the processing power of that particular mobile phone for neural computation in the forward pass. That's what I think. That's very interesting. A lot of business opportunities are there. So you can think about that also. For example, now if you assume that in this 3D area, you take an image and you may make a 3D model out of it using some online software and print it using a laser, using a 3D printer, and you can sell it. You can, if you have some artistic skills, you can do some painting also and sell beautiful artistic products. And you know that online business is there. If you advertise sufficiently, you can get business. I'm involved with the 3D business. I showed you this also, where the person types the name David Smith or something, and then textually the flat thing is generated. It's shown in 3D on the website, and then it's laser cut on a machine in the UK. And people order them, and people get these things and to give their loved ones and so on. The name-based name necklaces. So that kind of a lot of businesses are there. Are there any UM scholars working on research areas with generative models? Can you give some information on such research topics? Generative models. I don't know what they call it. Generative. We have one project where we try to DeepSeek, they use the so-called mixture of experts model. So we have a mixture of LoRa experts. That means you have the large language model or the vision language model. You have a large number of small experts that are uh, LoRa models, LoRa adapters. So we are trying to see whether we can plug these adapters one at a time to increase the things that this original large language model can do. And also we can try to see whether we come up with an adapter that can do safety for this, safe generation. So I don't know whether you call it a generative model, it is generative. So that is there. If you're talking about image generation, we do not do that. We did a 3D Gaussian splatting project. So the paper is there, but the paper got rejected, but paper is there online. This work. That's I don't know whether you can call it generative, but this, oh my goodness, the images are also extracted with that. Oh my goodness, some people wrote an article on our work. Yeah, this is our work. It's an AI generated article or something. But maybe that's an AI generated article. This is our article. That's a 3D. There is no generative model again. There is another project we are doing. We are generating a data set for 4D human actions. 4D human actions. That means actions progressing in a video. We are generating that data set and we are trying to classify them using point cloud. So that's also not generative exactly. Yeah, I never did that. I think I don't have too much knowledge also on that area. Yeah. In the electronics department, I don't think there's image generation, video generation, that kind of thing happening. They're worried about hardware, I think. I have about 10 GPUs, but that's not enough. Maybe it's not coming. Of course, if you want some discussion, of course, I'll be very happy to discuss. If the topic is of this nature, I'm very happy to discuss. Any other questions or comments?